We're going to continue with the knowledge area chemical change, and we're going to deal with ions in aqueous solution and the interaction and effects. Aqueous solutions are essentially solutions in which water is a solvent. As you know, most chemical reactions that take place around us involve substances dissolved in water. Right? Nutrients dissolved in blood are carried to our cells where they enter into reactions that keep them alive. Right? If it wasn't for water and transporting these electrolytes, there would have been no life. About 55% of the blood is made of water. That's just to give you some information. Now let's look at the general properties of aqueous solutions. A solution is a homogeneous mixture of two or more substances. The component present in the greater quantity is known as a solvent, and the other substance is known as a solute. Right? In a solution you have a solvent and a solute. Right? Water as a solvent. Let's look at some of its properties. Water is the most abundant compound on earth. It has the ability to dissolve a wide variety of substances, and it's rare to find pure water. The fact that most substances can dissolve in water, you hardly get water in its pure form. Solutions of water in which water is a dissolving medium are called aqueous solutions. We're going to be interested in aqueous solutions. At this stage, we are not worried about what happens when substances dissolve in ammonia, liquid ammonia, or in liquid ethanol, or in liquid methanol. We're not interested in the other solvents. We're only looking at substances dissolved in water. So, if we look at chemical reactions here that take place in water, there are chemical reactions that we are going to be dealing with in the next lesson, and those are precipitation reactions. They are acid-base reactions, and they are redox reactions. These are important reactions because most of these reactions take place in water, and the compound water is has polar molecules. Now let's zoom into the microscopic world and let's look at the Lewis diagram molecule. If we look at the water molecule, we know and we have learned that oxygen is in group 6, so it has 6 valency electrons. And hydrogen is in group 1 and it has 1 valency electron. So what happens if we apply the octet rule? We see that oxygen then has 8 electrons around the oxygen atom, but that's essentially just a rule which helps us to complete the Lewis diagram, and it gives us an indication of how many bonds between the respective atoms. So here you have there a pair, and there they share a pair, and these bonds are covalent bonds. They are actually covalent bonds. Right. So oxygen and hydrogen share a pair of electrons, but what we do know that the shared pair of electrons aren't equally shared between oxygen and hydrogen. What gives us an indication of the measure of the attractive force for the shared pair, right? There are various scales, but we'll look at one scale here, and let's see the electronegativity of hydrogen and oxygen. Right, if we look at electronegativity here, there's a data sheet that's going to be given in the exam as well. So you got your electronegativity. It shows you that copper has an electronegativity of 1.9. And if we look at hydrogen, it has an electronegativity of 2.1. And we're looking at then oxygen, which has an electronegativity of 3.5. Alright? So oxygen has an electronegativity of 3.5 and hydrogen has an electronegativity of oxygen has an electronegativity of 3.5 and hydrogen has an electronegativity of 2.1. These numbers merely give you an indication of the tendency that a particular atom has to attract a shared pair towards it. Right, now we know that the electrons are not, the shared pair aren't equally shared between the two atoms. So when we look at this, I could represent this instead of writing the electrons, I will just represent this in terms of let's say oxygen there, and we have one bond there, so that indicates that line indicates a shared pair of electrons, and here another shared pair of electrons, and then we obviously have our two non-bonding pairs there. And then the electronegativity difference here, we know that hydrogen is has an electronegativity of 2.1 and oxygen has an electronegativity of 3.5. So the electronegativity difference is equal to 3.5 minus 2.1, and that gives us 1.4. Right? Which tells us that the oxygen attracts the shared pair more towards it than hydrogen. And because of that, we find that the one end of oxygen becomes slightly negative, and the hydrogen is slightly positive, and that end is slightly positive. So here we have water, and it is a polar molecule. It's neutral, but it has ends that are slightly positive, like oxygen, and hydrogen has is slightly positive. So this is a polar molecule. Right. You'll learn more about polar molecules in grade 11. So now, but how do we, at the micro level, we say that the oxygen is partially negative, the oxygen atom, hydrogen is partially positive, but how do we demonstrate this at a macroscopic level? There's various experiments that can be used to show that water is a polar molecule. But I'm going to show you one that is simple to do. You can do it in your at home. You can do it in your kitchen, and it's quite simple, and it's fascinating in a sense. So let's look at, here we have a tap with running water, right? And let's say, for instance, you have a comb and you rub the comb through your hair. As you rub the comb through your hair, you find that, and if you bring the comb or a plastic ruler near the water, you find that the water gets attracted to the ruler comb. So let's assume here we have a ruler or a rod which is negatively charged. So when it's negatively charged, there are still positive charges here, but it's just that the negative charges are in excess, so the positive charges haven't been shown. But as we've illustrated, that water is a polar molecule, and we find that as we bring this particular rod or ruler near the water gets attracted. Now, how do we interpret this? In order to interpret this, we know that water has hydrogen and oxygen, and I'm not going to show the dots here now, or the electrons. So we know that N is partially negative and this N is partially positive. So what happens, because this rod is negatively charged, we find that the positive ends of the water particles get attracted to this particular rod. Let's look at the next one. If we look at this one here, again you got water running through, and this time you've got let's say a rod that is positively charged, but we know that it has negative charges. Only thing is there are more positive than negative charges, so we say that the rod is positively charged. Again here you'll find the negative end of your water molecule gets attracted to the rod. So here in this case you will see that you got that and you got that, and you have that, right? And that end is slightly negative, so your oxygen actually gets attracted, the oxygen part of your water molecule gets attracted to the rod, right? So that's how we interpret it. And so which means if you got this water molecule that has polar and non-polar areas, it tends to attract regions of opposite polarity, right? So your negative end of your oxygen gets attracted to the positive rod. In another situation, you have your positive end of hydrogen getting attracted to the negative rod. Right, now let's look at electrolytic properties. So let's say, for instance, we have two substances. We have sugar and we have salt. and they both dissolve in water, right? When they both dissolve in water, we know that we get clear solutions. Just looking at it from a macroscopic viewpoint, we will not be able to differentiate which substance is salt, which is a salt solution or which is a sugar solution. We wouldn't be able to do that unless we conduct further experiments. So how do these substances differ? One that might not look too obvious is we look at the electrical conductivity. Salt solution actually conducts electricity and sugar solution does not conduct electricity. Right, so immediately see, well, why does salt solution conduct electricity but sugar solution doesn't? Again, to get the answer, we need to zoom into the microscopic domain in order to interpret what happens at a macro domain. So whether or not a solution can conduct can be determined by the electrical conductivity. Alright? So when we're dealing with electrolytes, let's just see, we say a substance that dissolves in solution and it conducts electricity is called an electrolyte. So if sodium chloride dissolved in water can conduct electricity, then we say sodium chloride is an electrolyte. So some substances can conduct electricity in solution and others cannot. Right? Those that cannot conduct electricity when they're in solution, they are referred to as non-electrolytes. So here we have a strong electrolyte. Right? It has a large fraction of ions that can move about in a solution. Non-electrolytes, no ions present in solution. And then weak electrolytes, there's only a small fraction of ions in solution. So, in order to have a better understanding of electrolytes and what conducts, which solution conducts and which solution cannot conduct, we need to look at the instrument or device that can measure conductivity. Here we have a schematic diagram for measuring conductivity. Right? I have, for instance, a battery, right? So you know we have a battery here, and that is the negative part of the battery, and that's the positive part. So the one is a negative terminal of the battery and the one is a positive terminal of the battery. Then here we have a bulb. We have a bulb. Okay, we have a bulb, and here we have an emitter, right? Emitter, we have an emitter, right? And an emitter measures electrical current, right? We know that. Here now we have a beaker, and the beaker we can put the solution that we want to test in this beaker. And then we have two electrodes. The electrode, so the electrode that's connected to the negative terminal is called a cathode. So this electrode is called a cathode. And this one here that's connected to the positive terminal is called a anode. One is a cathode and one is a anode. Okay, so here we have this instrument. There's a battery, and there's a positive. You can see it's connected to the positive terminal, and the negative electrode is connected to the negative terminal. And the one that's connected to the negative terminal is called the cathode, and the one that's connected to the positive terminal is called the anode. Right. Now, these electrodes that we have here, they are essentially made of, you can have different types, but these are sort of graphite electrodes. Right, and we know graphite can conduct electricity, isn't it? I mean, we looked at the difference between graphite and diamond, and in graphite we said that we have delocalized electrons, so it can conduct electricity. Right, now let's look at, let's say for instance, if we look at now, let's say I'm looking at a solid, right? And let's say A, let's say it's wood. Let's say B could be a piece of string. And let's say C could be copper wire. Right. Now let's assume that we do not have the beaker there and there's no solution in the beaker. So for instance, if I then connect a piece of wood from the cathode to the anode like that, let's say I have a piece of wood that I connect from the anode to the cathode, and I look at the ammeter, it will show no reading. If I look at the bulb will not be won't light up, right? So we find that nothing happens. If I then substitute that, with string, and let's say that's B, the same thing happens. I mean, they do not conduct, there's no current flowing into that, in that circuit, because wood and string are not conductors, they are insulators, so it doesn't allow the current to flow through in the circuit. But if I now put copper wire here, if I put copper wire here, and then if I look at my bulb, I find that my bulb lights up, and there's a reading on my ammeter, which indicates that the current is flowing. Now we know when a current is in a circuit, there has to be a complete circuit, right? And the current needs to be able to move from the negative terminal to the positive terminal of the battery. So now if we look at, let's say instead of looking at solids, let's look at a solution. Right? If we look at a solution now, let's say for instance, we can say A, we look at a solution and we take for instance, let's say C, we take C6, right? Then we take CH3OH, we know that's methanol, and then we say NaCl. We could take another ionic substance also, let's say Na2SO4, right? We have these substances and we say, all right, now let's see if we, for instance, if we now have the water in a beaker and we add to it A, which means we add to it right? We add to it A, I'm having technical problems here. Say I have A in there. Right, when I have A in there, I see that if I have A in here, okay, I see, well, and it's dissolved in there, I've got sugar in there, so let's say, and I look at my emitter, and I see no reading, and my bulb hasn't lit up. Now we know sugar C6H12O6, right, or sucrose, it's a molecular substance, right? We know it's a molecular substance, so we don't see any the bulb doesn't light up and the emitter shows no reading. So from there we say, okay, there are no ions. Remember, in an electrolyte, for there to be conductivity, there has to be ions. Right. And then if I substitute that and I put B here, again I find that the emitter, there's no reading, and the bulb doesn't light up. But when I have sodium chloride dissolved in water or sodium sulfate dissolved in water, I see, if I take that and I put C there, either of the two, I find that yes, I see the bulb burning when I put C there, and my emitter will show a reading. So when we look at this here now, we say, in this case, when I have C, there are ions in solution. Right, so when we have now C6H12O6, we know that is a molecular substance. And even if we have methanol, it is a, sorry about that, it is also a molecular substance. And sodium chloride, we know that is an ionic substance. We've dealt extensively with this in our earlier lessons. What are molecular substances or molecular solids, and what are ionic substances? The reason so much time was spent on it because it has implications for when we're dealing with aqueous solutions. So you need to be able to recognize firstly from a formula whether we're dealing with a molecular substance or an ionic substance or a network covalent substance. Right, now the important thing here is, let's look at this. If we look at when sodium chloride is dissolved in water, we find that the bulb burns. So how do we explain that? Firstly, in the external circuit, so let's say this is the external circuit. The external circuit. There's the external circuit, right? In the external circuit, we find that electrons are moving. Electrons are moving, right? They move, and electrons are moving. Okay. So in the external circuit, you got electron conduction, or there's a current flowing. But here in the solution, you have ionic conduction. Ionic conduction. Right, you have ionic conduction. So what happens here is you have your Na plus, and Na plus, you know, is a cation. So the cation moves towards the cathode. And we know sodium chloride, it has a chloride ion, and the chloride ion moves towards the anode. So within the solution, you got ionic conduction. That means your ions are moving, and in the external circuit, you got electrons moving. So your circuit is complete. Because essentially, what's a current? A current is a movement of charge. In the external circuit, you've got electrons moving, and in solution, you've got ions moving. Right, now, let's look at the device for detecting ions in solution. Here we have, for instance, a device here which shows you again, if we have, for instance, ethanol, right? There's no conductivity. We know ethanol is CH3CH2OH, right? So it's a molecular substance, and here, although the space filling model gives you only sort of 2 atoms showing there, but what it's illustrating is that we're dealing with a molecular substance. Here, there's no conductivity. Here in this one, when we have KCl, there's high conductivity. Why? Basically because we have ions. You can see the negative ions going towards the positive plate or the positive electrode, and the positive ions moving towards the negative. So you got ionic conduction in the solution. And in the external circuit, you got electrons moving. Okay. Then, if we look at acetic acid here, acetic acid, we know it's CH3COOH. That's acetic acid. So acids do conduct electricity. Although this is a molecular substance, it conducts electricity. Acids conduct electricity, and we'll talk about that a bit later. Right, so that's vinegar, and if we put it in the cell, we find that it conducts electricity. Right. Now let's look at the device, the same device again, but measures the flow of current. Here in this case, here you see you've got a bulb again. So here you have a non-electrolyte, right? Because the bulb is not burning. There it's a weak electrolyte because the bulb is dim. And here we got a strong electrolyte because the bulb is bright. And where a non-electrolyte, there's no current flows, and when it's a weak electrolyte, some current flows, and when it's a strong electrolyte, a lot of current flows. So the current in a circuit gives you an indication of what is happening in the solution, right? The rate at which those ions are moving from cathode to anode. Right, now here we have same again conductivity of solutions, but here we're looking at acids dissolving in water, right? Acids dissolving in water. Now mostly acids have an H, right? H in front, there's an H, there's an H. All these are referred to as acids. So from the formula, you should be able to recognize whether we're dealing with an acid or not, right? Although these are molecular substances, but they're different in the sense that they are acids. And because they're acids, they sort of when they dissolve in water, they form what we call electrolytes. And if they form electrolytes, what's it telling us? This is a molecular substance. HCl is a molecular substance. If it conducts electricity, that means that in the solution there are ions, right? So we need to see where we have a molecular substance that dissolves in water and can form ions. There are other molecular substances that dissolve in water and they do not form ions. So acids, when they dissolve in water, form ions. Right. You will notice here this one, that one there is actually acetic acid. So we know acetic acid is CH3COOH, right? So it's not entirely obvious that this is an acid. It is an organic acid. So what we do is we put the H in front and we say CH3COO, and that gives you an indication just from the formula that you can recognize that it is an acid. Okay, now let's look at the flow chart, right? That looks at when these substances, the water soluble compounds, right, of electrolytes and non-electrolytes. So if we look at this and we look at the substance, let's say we have a substance here, substance, right? And if you look at the substance, we say right, and we say that, and here we say molecular, let's just get rid of that there. Let's draw it a bit better. So let's say that is molecular, right? And let's say that is ionic, right? And if we look at this, so let's say we have that and we have that, right? And let's say molecular substance if it's an acid, okay, and or let's just maybe write a formula for an acid. So let's say HCl, and this side we got C6H12O6, and we have maybe CH3OH. And what we know, if it's a molecular substance and it dissolves in water, here we're going to have it's going to form an electrolyte. And here these form non-electrolytes, right? And here in this case it forms an electrolyte. Right, and here since it forms an electrolyte, it is dissolved in water, HCl, it's an electrolyte, so we know there are ions involved. Here there are no ions involved. And here we know there are ions involved. So whenever there's ions in solution, that gives us an indication that the solution will conduct. Right, now let's look at an exercise. It says indicate whether the following is an ionic or a molecular substance. Right, KCl, you know, we did that. It's metal plus non-metal. That's ionic. If we look at the C6H12O, they all non-metals, so that's a molecular substance. Here, K2SO4, again you got a metal with the sulfate anion, so this is ionic. CH3OH, we know it's all non-metals there, this is molecular, and we saw that it does not conduct any. The solution, it's not an electrolyte, right? So there's no ions in solution. NaOH, we know that this is ionic, right? And since it's a Na in this substance, which is plus, and OH, the hydroxyl ion, which is minus. HCl, right, it's, we just look at it, it seems to be molecular. Yes, it is a molecular substance, but it's a molecular substance that's an acid. So it's the substance is molecular, so the substance is molecular, right? It's a molecular substance, all right, but we know that it is an acid. Aluminum nitrate is ionic. HNO3 is also a molecular substance, right? But it has its H there, and that one had H there, and from the formula we know we also dealing with an acid. And the same thing with HBr, it is also a molecular substance. Right, and we have the H there, which is also then also an acid. Okay, so now let's look at reactions in aqueous solutions. Firstly, substances that dissolve in water to form solutions. We can have ionic substance and we can have molecular substances. I've already alluded to the polar nature of the water molecule, right? We're going to look at the idea of hydration. And then we're going to look at balanced equations when substances are dissolved in water. Ionic and molecular substances, and we look at the state of reactants and products. And as you could see, we're looking at things and we're explaining certain phenomenon in terms of what happens at a macroscopic level and at a microscopic level. Now let's look at dissolution, right? Or dissolving is a process where ionic crystals, right? Ionic crystals break up into ions. So we know we've dealt with ionic substances like NaCl is an ionic substance, sodium carbonate is an ionic substance, NaOH is an ionic substance, calcium hydroxide is also an ionic substance, but when you see an OH in the formula here, that gives us an indication that we're dealing with bases, right? It's an ionic substance, but these are bases and they have special properties which you are going to do in the subsequent lessons. Then we have molecular solids dissolving in water. So here we have, for instance, that which we checked, and there we saw that, and acids, right, which is nitric acid and hydrochloric acid. Right, but we want to see what happens when these substances dissolve in water and what happens at a molecular level. So if we look at the ionic substance in water, so the dissociation is a general process in which the ionic compound separates into ions. So we know that, for instance, if we had NaCl, correct, and we saw this lattice, and I'm going to still show you, but let's just look at this, and the sodium chloride is made of Na ions, and we know it's made of Cl ions, right, chloride ions and sodium ions. Ionization of a molecular substance in water, right? So the ionization here is a process where molecular substances like acids form ions when they dissolve in water. So, for instance, if we look at now HCl, what happens is HCl and especially acids, when they dissolve in water, they form ions. So that and that. Now remember, HCl is a molecular substance. There are no ions involved here, but we do know that the hydrogen and chlorine share a pair of electrons between them, and they unequally shared because chlorine is more electronegative than hydrogen, so it attracts the electrons more towards it than hydrogen. So that end becomes partially negative and that end is partially positive, and when this is in solution, you find that ions are formed, right? Remember, the molecule doesn't have ions, unlike an ionic substance. An ionic substance, the solid itself has ions already. Only thing is, the ions are not mobile. And the concentration of ions in water is a measure of is a measure of its conductivity. So the more ions you have in water, the greater the conductivity. And concentration is what we will be dealing with in the subsequent lessons. Concentration is essentially gives you an indication of the number of solid or solute particles per unit volume. Right. Right. Now solubility also is the amount of substance that dissolves in a given quantity of solvent, right, to form a saturated solution. That's what solubility is. But solubility is not always a measure of conductivity. Right. And we've illustrated that. For instance, if I take sucrose and I dissolve it in water, it's more soluble than sodium chloride, right? More of the sugar can dissolve in water than the salt. And so it doesn't mean if something is soluble, it will have a greater conductivity. Right, so let's just summarize that. So let's say, for instance, if we look at the conductivity, and we say, all right, conductivity, there is a measure of, right? If we say, gives us an indication of the type of solid, right? It's also a measure of the concentration, as I alluded to, and it also depends on solubility. Also depends on solubility. Right? It does depend on solubility, but not always. Okay? Certain substances, the more soluble it is, the greater conductivity, but it depends on the type of substance. Right. Okay. Now let's look at dissolving of an ionic substance. Right. So if we look at a macro level, here, we've got salt, right? It's an ionic substance, and that is how salt looks, right? So this is your salt, and that is how it looks. Okay, now let's see what happens at a micro level. We have seen this before, and we know that the salt is made of chloride ions, correct? And the smaller ones, they are sodium ions, right? How do we know? We know that the ionic radius of the sodium ion is smaller than the chloride ion, so the larger ones are the chloride ions. So here you have these sodium and chloride ions extending over this entire framework. So that's a microscopic description. If we look at it in terms of a lattice, then we know that here we have our Cl Cl minus, and there we have Na plus. Right, now when this particular substance is dissolved in water, and we have just spoken about water, I've shown you that water has polar molecules. So having polar molecules, the substance water is actually a polar substance, and which means that it has that and that I showed you, and this end is partially negative, and these ends are partially positive. So you saw what happens when I bring a charged rod to water, right? The water gets attracted. Now in a similar way, you're going to find that the positive particles will get attracted to the oxygen part of the molecule, and the negative particles will get attracted to the positive part of the molecule. So partially positive, since this is negative. That's negative. Right, so what happens is that the water molecule tends to attack attack these ions on the surface, and it then breaks it down. So here we look at it. Ions hydrated. What is hydration? Hydration is the process where ions become surrounded with water molecules. Now here we have, for instance, our solute, which you see. What happens here? You will see that your positive particles are hydrated, right? As you can see, the negative end of your water molecule is surrounding the positive particle. And here, in this case, you got the positive end of your water molecule surrounding the negative ion. So we say that these ions are hydrated, right? They're hydrated. Which in a sense, what happens is, since they're hydrated, these ions do not recombine to form the solid again. Right, so this is how it dissolves, and as it dissolves there, this is how we interpret it. We say, right, we got sodium chloride, like that, which is a solid. And when it dissolves in water, we normally say, okay, H2O, since our liquid is water, and that gives us Na plus, and we say aqueous, and we say plus Cl minus, and that we say aqueous. What aqueous really means is that it's in a water environment. So the solid, when dissolved in water, it breaks up, and the ions are then hydrated, and you have sodium ions and chloride ions. So these are the ions in a solution that can move, and therefore and it forms an electrolyte. When sodium chloride dissolves in water, it's considered to be an electrolyte, and these ions can then move. Right. If we have other ionic substances, let's say for instance I have Na2SO4, again, if that's dissolved in water, sometimes we can put water there, and that would then say Na plus aqueous plus SO4. We know what the charge of that is, since you know what the charges of these polyatomic ions are. But here, if we look at it, our equation is not balanced because we've got two NAs on the left and only one on the right. So we need to then put 2 here, and we are then happy because we got 2 NAs on the right and 2 Na on the left. And in terms of charge, you got 2 positive charges and sulfate, which has a 2 negative charge, so that's neutral. So our charges are balanced and our atoms are balanced. Let's look at dissolving of a molecular substance. Molecular substance, here I've got sucrose. Here you'll see, okay, you have sucrose here, right? And all that. And what happens in this case when it's dissolved, you got all your water molecules and your sucrose molecule is interspersed between these particular water molecules. So here we don't have any ions. There aren't any ions. They are discrete molecules in here. The water molecules and the sucrose molecules are discrete. And if we have to represent this in an equation form, I would say C6H12O6, and that's a solid. And what happens if I have water here? All I can say is that I've got H12 and H12 and O6, and we say it's aqueous. That means that the sucrose has dissolved in water, and the fact that we write aqueous there, it indicates that it's in solution, right? So whenever it dissolves in water, we put down aqueous to show that it's in water environment and it is dissolved in water. Now let's look at another one, dissolving of a molecular substance, but this time we're looking at methanol. Again, methanol, there you got methanol, because methanol, remember, is CH3, so you can see CH3OH there. Then you got your water molecules, your methanol, your water molecules, and it's not like as if the water molecules are surrounding any ion, right? So they all are the water molecules and methanol molecules are spread out in this particular solution. So if we look at this now, I would say here CH3OH, and that's a liquid, and if it's dissolved in water, I don't have to write this all the time, and I can say CH3OH, and we say it's aqueous. That means it has dissolved in water, and in water, when the ethanol is dissolved, it's essentially in solution. There are no ions formed here. Now dissolving a molecular substance. Let's look at acids are also molecular substances. We spoke about that, right? But different to that of sugar and methanol. And we recognize an acid from its formula. I showed you earlier, so we know acid's got H, and when we look at that, just from the formula, we recognize it as being an acid. Surely, I mean, you did this in the earlier standards at an observable level. How would you identify an acid? We would at a macro level, we will take indicator paper, and if indicator acid turns blue litmus red. If the blue litmus becomes red, then we say, okay, that particular substance is an acid. Here you're recognizing it in terms of its formula. Right, now if we look at Lewis diagrams showing water reacting with an acid. Right, so if we look at that, where we looking at HCl. Now if we look at, say, the Lewis diagram for HCl molecule, in which H plus is released and then reacting with a molecule of water, right? So let's just see what we're talking about here. If we have, for instance, HCl, right? HCl, we know now, for instance, if I got chlorine, we know it's in group 7, so it has 7 valency electrons. And if I look at hydrogen, hydrogen has 1 valency electrons, and we know that we get a bond. Again here, because the electronegativity difference between chlorine and hydrogen is the electronegativity of these atoms is different, we find that the shared pair is attracted more towards chlorine than hydrogen, since chlorine is more electronegative than hydrogen. Hydrogen, we know, has an electronegativity of 2.1 and chlorine has an electronegativity of 3.0, right? You can check that out in a periodic table. I remember it because I work so much with these electronegativities. So in this situation, you find that your one end of your chlorine is partially negative and that end is partially positive. Right, so it's a polar molecule as well. One end is partially positive, one end is partially negative, so there are no real ions. It's just that one end is slightly negative and the other end is slightly positive. But when these molecules are dissolved in water, what happens is, we know that water is a polar substance as well, and then what happens is the HCl becomes H plus and Cl minus. So the HCl molecule didn't have any ions, but when it dissolves in water, the hydrogen breaks off from the hydrogen chloride and it forms an ion. So when these acids dissolve in water, they break up into their ions. So if we look at this and we say, all right, that's what's happening at the molecular level. If I want to represent this HCl, and I say, okay, this, when it's dissolved in water, it's HCl and it becomes H plus aqueous plus Cl minus aqueous, saying that these ions are in solution. If we take another example and I have HNO3, right, aqueous, again could be saying H plus aqueous plus NO3 minus aqueous. Right, so the hydrogen is in water. But now what we have is that normally we say the hydrogen in water doesn't exist on its own. What happens? It reacts with water. So sometimes we say, okay, H plus. This is not directly relevant now, but it is going to be when you go to grade 11 and 12, and you got your water molecule here. And we got that as our H, and that as our H. So this particular hydrogen ion becomes stabilized by bonding with OH, and we then have OH, we have H, and H, like that, and that forms a ion like that. So this particular ion is known as a hydronium ion. Hydronium ion. You're going to use that quite a bit when you're dealing with acid bases in grade 11, right? So in solution, the H plus really exists as a H3O plus. Okay? Alright, now let's look at here. It gives you an indication. Here you have your HCl molecule, and in solution, as you can see, you're getting chloride ions and you're getting hydronium ions, right? There you got your hydronium ions, and chloride ions. So as you can see here, it's showing you when HCl dissolves in water. So we write, so if we have HCl and we want to show that the acid releases the hydrogen ion, so we say it's that plus we say it's Cl minus aqueous. An alternative way to write it, we say HCl plus H2O, and then we say since this H plus gets donated, it becomes H3O plus Cl minus. So that's aqueous and that's aqueous. For our purposes, we are only going to look at this when it's in water. Okay? In the subsequent grade, we'll look at HCl and how it reacts with water to give us hydronium ions. So hydronium ions, it depends whose model we are using. You'll get to that, whether it's an Arrhenius model or whether it's a Bronsted-Lowry model, right? But for now, when an acid dissolves in water, you need to be able to write it in that form. Right, now write an equation showing the dissolution process in water of this substance. So here we're going to say KCl solid, and that gives us K plus aqueous plus Cl minus aqueous. If we look at this one, we know that's a molecular substance, so C6H12O6 solid, and in water that gives us C6H12O6, and that is aqueous. It stays in a molecular form. This is again an ionic substance, so it's going to be K2SO4, right? The solid, when that breaks up and it's in solution, so you'll notice I'm not putting water there, that is then becomes K plus SO4 2 minus, and that is K plus, and to balance it you got 2 on that side, 2, so your potassiums are balanced and your charges are balanced. If we look at this, CH3OH, that's your liquid, and in this case we then if it's in water, which becomes CH3OH and aqueous, because it dissolves in water, so we're showing it as aqueous. Here again we got this ionic substance, but this is a base. Remember I spoke about it earlier, I referred to it earlier. So here we got NaCl, sorry about that, NaOH, which is our solid, and that gives us Na plus aqueous, and we know the hydroxyl ion is negative. Right? And if we look at HCl, so HCl, the gas, and if it dissolves in water, I said we'll use this, right, and we say Cl minus, right, in aqueous solution. Remember I said H plus exists as a hydronium ion in water, but that's not for us at this grade. Then you got AlNO3, right, the solid, and we know that's an ionic substance, right, so that gives us Al. We know what the charge on it is, right, because we've done that intensively and extensively, plus NO3 minus. So as you can see, right, and in here you'll notice that the charges are unbalanced, so we need to add a 3 there. So here I got 3 negatives and 3 positives, so the charges are balanced, right? And I say aqueous, and I say aqueous. Okay, then we have HNO3, it's our liquid, which then gives us H plus aqueous plus NO3 minus aqueous. HBr, again, it's an acid because we recognize this as an acid, and HBr, our liquid, when it dissolves in water, gives us H plus aqueous plus Br minus aqueous. Okay, there you have it so far. Now let's look at this. Identify each of the following substances as an electrolyte or a non-electrolyte. So here we have that is a molecular substance, so it's a non-electrolyte. Okay, electrolyte. Here it's an ionic substance, it's an electrolyte. Okay, surely you'll have to do that conductivity test, because sometimes what happens is some of these ionic substances are not soluble in water. So they may be ionic but they're not soluble, but most of the ones we're dealing with, they're soluble in water. So here electrolyte, again, because it dissolves and it forms ions, right? And predict which will conduct when dissolved. So non-electrolyte, this will not conduct, right? Not conduct. Okay, that won't conduct. Thus, we're predicting it will conduct. It's an ionic substance. Thus, we're predicting it will conduct. Right. Thus, it also forms an electrolyte. Right. We wouldn't have thought so, but because it's an acid, we know that an acid ionizes, so it will conduct. Right. It doesn't have ions, it's a polar substance, but because when it reacts with water, ions are formed in solution, so it conducts. Okay. So, KOH is also an electrolyte. And it will conduct. Forms an electrolyte. Here I showed you acetic acid, and in this case also it forms an electrolyte. You can see it's a molecular substance, but it's an acid, so it conducts. So what are the principal solid species present in the aqueous solutions of NaI? So there the principal would be Na plus plus I negative, right? In this one here, it would be Ag plus CO3 2 negative, right? I haven't balanced them, okay? I'm just giving you an indication of what we have, but so we have the principal species here. Here, ammonium phosphate, right? Now here you can see we have like a molecular substance. Now you would think, oh, this is a molecular substance. Yes, in terms of how we said that nonmetals form molecular substances. But here, when we're dealing with ammonia, this is a slight difference here. This actually is an ionic substance, right? Why? So NH, you have NH4, which forms plus, and plus PO4, which gives us 3 minus. So you'll remember when you had to learn your polyatomic ions, ammonium had a plus charge, and PO4 phosphate has a minus charge, 3 minus charge. Right, so it forms an ionic substance. So it forms an ionic substance, but within the ammonium ion, the nitrogen and the hydrogen are bonded covalently, right? And then here our would be 2 plus SO4 2 minus. Right, so here for instance, what test would you carry out in order to ascertain whether it's a molecular substance or not? You dissolve it in water and see if it conducts electricity. Then it's an ionic substance. That means there are ions present in there. Okay? And then we got K2CO3, which means K2CO3, which in this case our ions would be K plus CO3 2 minus. Okay, I'm not balancing it like I said. And then HCl, our ions would be H plus Cl minus, right? And let's go back. Alright, the principal ions, okay, we've got that. If we want to, we could just perhaps, if we want to just balance it, we can balance that there and here. We could balance that, and here in this case if we balance it, it would be then a 3 there, right? So it means 3 positives and 3 negatives, right? If we want to balance it. And there we have it. I'll see you in the next lesson, and where we will be using most of the things that we have learned in this particular lesson.